Yeah, welcome. So, today is our second lecture and it is on the overview of voltage regulators. So, in this lecture we are going to discuss about the linear voltage regulators, then introduction to switch capacitor converters, then hybrid switch capacitor converter basic understanding, and then the basic switch mode power converter. So, the voltage regulator, if you start from very basic, that means it start with a simple voltage resistive divider, where we have a series resistance Rs and load resistance R, and the voltage across the load resistance is simply R by R plus Rs. Now, here what can happen? Here the input voltage can vary, the load resistance can vary, but we need to regulate the voltage. So, in order to regulate the voltage, what degree of freedom we have in our hand is the variation of the source resistance. So, we can vary the source resistance in a way that output voltage is maintained at its desired value in spite of variation in input voltage and or in load resistance. But if we try to look at the efficiency of this voltage regulator, its theoretical efficiency is same as the voltage conversion ratio, which is V0 by Vn, but practically even it will be less. That means, if you want to achieve higher voltage conversion, your efficiency will get degraded significantly, because the most of the voltage drop across the Rs will be dissipated as a heat energy. So, if you want to achieve lower voltage as V0, then the maximum voltage, that means Vin minus V0, that voltage will be dropped across the series resistance, and higher this drop voltage, lower the efficiency, and also higher the I square R loss. So, temperature will go up. So, this process is not a very efficient way of regulating output voltage, and in general this variable source resistance can be achieved by using a transistor. This is a more practical dropout regulator, linear dropout regulator, where what we discuss, that we want to drop certain voltage across the series resistance such that the output voltage is maintained at its desired value. So, we want to use a transistor which will act like a variable resistance, and how can we adjust the resistance of the transistor? By varying the gate voltage, and for gate voltage, the input for this gate drive is the feedback voltage of the output feedback voltage. We generally put a resistive divider, and then we need to compare with the desired reference voltage, and accordingly we will generate the gate voltage such that the output the drop across the PMOS transistor, here we are using PMOS, is drop is created in such a way the output voltage is maintained. And here we also use input capacitor and output capacitor in practical linear dropout regulator. So, what are the advantages of this linear voltage regulator? The advantages is that this is very simple, that means it's like a resistive divider, very simple to analyze and design, relatively simple. In transistor level it can be somewhat more challenging, but in general from system level these are simple, and these are used for ultra low power applications in which the current requirement in the output is very low, such that the current going through the series resistance will also be low. So, that the I square R loss will be low. Even though it is not very highly efficient, but we still need to limit the losses across the resistance, because that it will dissipate, that loss, the power loss will be converted into heat energy and it can heat up. So, low power, that heat can be maintained. because it has negligible switching noise, because there is not much switching, what we will be discussing in subsequent voltage regulator, where there will be inherent switching. So, here it is less susceptible to switching noise. So, as a result the EMI is low, and also the design can be made compact using an integrated circuit. But what are the disadvantages? As we discussed, the efficiency is very low and it depends on the dropout voltage. Higher the dropout voltage, the lower the efficiency. In fact, if we want to step down, let us say from 12 volt to 3.3 volt, generally one such voltage regulator is not recommended. We should use more than one, so that if the first stage it can be 12 to let us say 8 volt, and the second stage 8 to 3.3, or even we can divide into multiple pieces, because at each stage the dropout voltage across the transistor should be smaller, so that the heat dissipation can be distributed among multiple stages. But as we increase the number of stages, efficiency further reduces. It also has a poor power handling, current handling capacity, because as I said, if we try to use it for higher current, then the losses will be really significantly higher and it will be unmanageable. And it is also very lossy at high power level. That means, if you have the load current vary, and if it is designed for a certain load range, it is good to use at lower current level. As the current level increases, then the losses increases. And third one, another drawback is that this is generally not used for step up application, it is just used for step down application. The next, we can use a shunt voltage regulator, where in addition, like compared to the series voltage regulator, we are considering an additional current shunt path across the load resistance IC. This is generally a control current, and in this case the voltage gain along with the R by R plus RS, another factor will come due to the current sinking path. So, the efficiency can be shown that it is even lower than the series voltage regulator, but because of this current shunt path, this gives an additional degree of freedom, and that helps to improve the regulation, voltage regulation, while dealing with a little bit a wider range of load current. So, a simplest application here, that example, simplest example, we can replace this current the IC, the current regulator, as a Zener diode, where the voltage across the Zener diode can be maintained, and whatever the residual current, there will be a load resistance, and that current, that means the Zener voltage will be constant, and the current passing through the Zener diode will be in such that the voltage across output voltage will be maintained. So, shunt regulator actually, since it has an additional current sink path, so it can offer better output voltage regulation, and these are common in voltage reference circuit, but not using Zener diode. They can use a transistor for using as a control current source. But as I said, its losses are more, or even the voltage gain, efficiency is lower than the series voltage regulator. Even if the load does not draw any power, due to the current sink path, there can be some additional losses even at zero output power. So, that means the efficiency is poor than even the series voltage regulator, and here also we cannot achieve step up voltage conversion. So, you have to think something using energy storing element rather than dissipative element to further improve the efficiency and also to achieve voltage regulation. So, one of the way we can use capacitive network, that means here we are using two capacitance, they are in series, and if we take the voltage across one capacitor, and it can be represented by the ratio of like a Cs by Cs plus C0, and that into input voltage will be the output voltage. But what is the problem here? The first problem, if there is any variation in the input voltage, if since the ratio is constant, the output voltage will vary. So, it has a poor line regulation. That means, any change in supply voltage will also affect the variation in the output voltage. I mean, it will lead to the variation in the output voltage. The another problem is that here we have not connected any load. If you do not connect any load, then the charge balance will happen in such a way that we can get the output voltage in terms of input voltage and the ratio of capacitance. But what happens if we connect a load? That means, we connect a load resistance across the output capacitance C0. We connect a load, then once we connect the load, we can write the equation like a simple, this equation is a very simple equation. In fact, it will show, it can be represented by a first order system, where the output voltage can be written as the initial voltage into e to the power of minus t by tau equivalent, or tau equivalent is written. And what we will see, if you wait for some time, that means when t increases, the output voltage start falling. What is the, why it happens? Because when you start drawing current, I mean the current is going through the load resistance, that means that current should come from the supply voltage. If that current comes from the supply voltage, that means the charge, rate of charge will actually change, rate of change of charge, that means dq dt, it is nothing but the current. Since the current is flowing, the charge is no longer constant, the charge is varying. If the charge varies, what happens? The source capacitance actually, because it is getting more and more charge, so it will, the voltage across source capacitor will grow up, whereas the voltage across load capacitance will comes down, and ultimately the voltage will become 0 at steady state. So, the voltage will collapse. So, such circuit cannot be used for a voltage regulator while considering a load, and of course, it has a line regulation problem. Then what is the next solution? How can you solve this problem? So, now instead of that fixed capacitance, what we considered earlier, what was our problem? Our problem is that the charge balance. When we are operating at steady state without load, the charge was balanced, but when you connect a load, the current is flowing and the charge balance is getting hampered. As a result, you have an asymmetric voltage across the capacitor and the output capacitor collapses. But now, suppose if we find a mechanism by which we can try to maintain the charge balance by means of a switching action, and that is exactly charge balance can be achieved using a flying capacitor, and by periodically switching back and forth this capacitor between source and the load output capacitor, and this Cf is the flying capacitor, and you can see there are 4 switches. In some cases, in fact, I will show you that you do not need even a source capacitance, because the flying capacitor itself can be connected between the output capacitance and the input voltage. So, that means the Cf can be connected in series with the load capacitance IC0 output capacitance, and it can also be connected across the load capacitance output capacitance. So, it can be connected, reconnected, and periodically back and forth connection between supply and the load, we can maintain the charge balance. So, basically in order to get a voltage balance, we need to do charge balance. So, this can achieve step down voltage conversion, and these are called step down switch capacitor voltage regulator. So, now we understood that flying capacitor can achieve certain, can achieve voltage balance, but again this is only when you connect that flying capacitor in series with the input voltage and the output voltage. That means I am talking about, if you, that means if you take this configuration, when S1 and S3 are on, that means I am talking about this switch and these switches are on, then this is connected, the flying capacitor is connected across the source capacitance, and if the source capacitance is not there, the flying capacitor is actually, if it is not there, then the flying capacitor is connected between the supply and the output capacitor C0, this capacitor, and it is now getting charged. Okay, but the moment we connect flying capacitor, the voltage will go, there is a discrete jump and it will reach V in by 2, that can be proved using charge balance equation. But if you wait for some time, then the same problem happen, the voltage across flying capacitor will build up and the voltage across output capacitor will go down, but the total voltage across the two capacitor will be constant, which is nothing but the input voltage. So, we need to quickly take this capacitor back and connect to the load capacitor, output capacitor. Again, when we connect the output capacitor, the next time again it will reach to V in by 2, and now the total capacitance are now connected to load capacitor, that means flying capacitor and the output capacitor. If this source capacitor is not there, that means if input supply is disconnected and two capacitors are actually supplying to the load. So, naturally they will get discharged. So, you cannot keep this configuration for long time. So, none of this, like a charging phase or discharging phase, should continue. In each of these phase, the output capacitor will discharge. So, we need to do it periodically and we need to do rapidly, so that this deviation around this input voltage by 2 can be reduced. It can be reduced and keep within a certain limit, but such frequent charging and discharging will also put a limit, that is called high frequency switching limit. Okay. So, we have discussed about two configuration. This one, the flying capacitor in one case is connected between the input voltage and the output capacitor, and the second case the flying cap is connected across the output capacitor. So, one is charging phase, other is the discharging phase. And what we found, this rate of discharge, that means if we talk about this particular profile, who decide this rate of discharge? So, the faster discharge corresponds to higher current that the output capacitor is delivering to the load. That means, if the load current increases, this rate of discharge will be faster. If the load current if the load current increases, the rate of discharge will be faster. If the load current decreases, the rate of discharge will be slower. So, that means this output voltage ripple is load dependent. So, it has a poor output voltage load regulation. That means, with the load current, the ripple voltage changes, and when we talk about the average voltage, that is my regulated voltage, that is my average voltage, capital V0, and that voltage varies when the ripple varies and when load current varies. So, output voltage also changes. So, it has a poor voltage load regulation. It also has a poor line regulation, because this V in by 2, this voltage which is the peak voltage, that is dependent on the input voltage. If the input voltage increases, this voltage goes up. If the input voltage decreases, this voltage goes down. So, if we want to maintain this voltage constant, then generally this voltage, this peak voltage is V in by 2, that means it can achieve voltage half of the input voltage. If you want to achieve higher step down, then we need to connect such cell, multiple flying capacitor cell. If you use 2 such cell, then you can achieve 1/4, 3, 1/8. So, it is 1 by 2 to the power into the number of cells. And regulation point depends not only that step down factor, it also depends on the rate of discharge profile. That means, the value of the capacitance, output capacitance. So, if you take a larger capacitance, then you can reduce this voltage ripple and achieve higher, better regulation. But again, larger capacitor has a penalty in terms of power density. Secondly, if you look from this to this configuration, when this flying cap was initially connected to the supply, this voltage was different than the output capacitor voltage. When you reconnect back, if the output capacitor is large, initially there is a voltage difference between the flying capacitor and the output capacitor. Flying capacitor is sitting at a higher voltage, whereas the output capacitor is sitting at a lower voltage. So, this voltage mismatch will cause a huge inrush current. That means, huge inrush current will go from flying capacitor to the output capacitor, and it is important to limit the current. So, as a result, we also want to make sure that very large voltage variation is not desirable, and also the amount of current also depends on the size of the output capacitor. So, if you have take a larger capacitor, that means the difference in the voltage is large. So, half CV, half C, that means if you take half C into V1 square minus V2 square. So, for the same voltage difference, if this capacitor is large, that means the energy difference will be large, and as a result the shoot through current, inrush current can be higher. So, that is why we have to keep in mind that this capacitor size also has a constant selection, and as I said, there is a inrush current during switching. Okay. So, in order, that means now we talk about step down switch capacitor converter. So, if you look at a basic switching cell, it has 3 terminal, the terminal 1, terminal 2 and terminal 3, and this is my flying capacitor, and there are 4 switches. Now, we can connect these 3 terminal in a different way to achieve various functionality, like you can achieve step down operation, you can achieve step up operation, even you can achieve voltage inversion like a inverter. So, I am just showing here 2 cases, one is step down and step up. I am not showing voltage like a voltage inversion, that is also possible. So, in step down we connect terminal 1 here, terminal 2 here, terminal 3 and terminal 2 here, and we set the switch S1 and S1 identically, they operate identically, S1 bar and S1 bar they operate identically, and S1 and S1 bar they operate in a complementary fashion. So, here if you, that means this particular step down converter we saw in the previous example, here we have eliminated the source capacitance. So, that means the flying cap, that means this is my flying cap, this flying cap can get connected in series with the input voltage and the output capacitor, and it also gets reconnected to across the load capacitance. That means, in the second phase, in the discharge phase, it is disconnected from the supply and connected across the output capacitance. In the other case, if you say step up, we rotate this cell in such a way, that means we change the interconnection, terminal 1 is here, terminal 3 is here and terminal 2 is here, and we set this S1 here, S1 and S1 bar here, S1 bar here. That means, when the switch is on S1, the flying capacitor, which is the flying capacitor, it is connected across the input voltage. In the next cycle, you turn on S1 bar switch and turn off S1 switch, then this supply, that means flying capacitor voltage actually comes in series with the input voltage and with a polarity such that the output voltage becomes input voltage plus flying capacitor voltage. By that way, we can achieve step up conversion. So, we can achieve both step up and step down voltage regulation, conversion. However, in all these cases, in these 2 cases, we can achieve whether step up or step down in a factor of 2. That means, one cell we are using this cell 1, now only one cell we are using. If you want to achieve, let us say step down is 1/4, we need 2 such cell. If you want to achieve step up of 2 like a 4, like a 2 square, we need 2 cells like that. So, we saw there are certain difficulty in pure switch capacitor converter because of we are switching back and forth switches capacitor with different voltage level, and that can lead to high inrush current. One way to avoid or to reduce this inrush current effect, we need to put a current limit. That means the current should not change drastically or immediately. We need to put a limit, slew limit, and we know in order to do that we need to put an inductor. So, if we redraw this circuit, the first circuit which is a step down converter, then if we add a small inductor to limit the slew rate of the current, then this inductor is connected here. This is the inductor, a small inductor, size is small. This inductor was primarily used to reduce the slew rate of the current, so that we can reduce the effect of high inrush current, and this can also achieve better regulation than pure switch cap converter. So, hybrid switch cap converter. So, this is called hybrid step down DC-DC converter, in which the primary energy transfer element still remains the capacitor, which can achieve high energy density, because the capacitor offer higher energy density than inductor, because it can store more energy with a smaller size, whereas the inductor here is a small inductor which is used to limit the current. It is not used primarily for energy storing or transfer element, that is why its value is very small. But if we want to go for on chip application, we can go for a higher switching frequency to reduce the flying capacitor value, and if the power level is low, the switches can be integrated inside the IC. But typically these inductance actually we consider either off chip, and if they are very small, even we can consider on chip inductance also. Now, what will happen for hybrid step up converter? We talk about hybrid step up converter, where it has 3 cell like a 3 terminal 1, 2, 3, and we have discussed, if we redraw this circuit, what we discuss initially, this flying cap, that means in the charging phase it is connected between this terminal. So, this is the connection. In the second phase, if we go for the second phase, this is connected like this way. Here it is connected, this way it is connected across this terminal. So, this is the second phase of this circuit. Here you see, when it was charging the red color, then the flying capacitor voltage, this voltage is positive and this is negative. So, it was getting charged to the input voltage. Okay. And just a minute. Okay. So, this is positive terminal, this is negative terminal. In the discharge phase, this positive terminal and negative terminals, again they come in series with the input voltage. That means, V in then flying cap voltage, if we add them together, that is equal to the output voltage. So, output voltage can achieve twice V in. Now, again if we add a small inductance, in order to reduce the voltage difference of the flying capacitor, that means if you want to reduce the inrush current, then you can add a small inductance, and this makes a hybrid step up DC-DC converter. So, that means we can achieve higher step up conversion by using hybrid switch capacitor converter, and at present these hybrid switch capacitor converters are getting more and more popularity. So, if we summarize, I mean we know about voltage regulator using resistive divider, and this we are using capacitive divider, and at the end we added small inductance, and which offer benefit in terms of regulation, which is better than pure switch capacitor converter. So, switch cap voltage regulator, they are more efficient and higher power, it can handle higher power than linear dropout regulator, and here we can achieve step up voltage conversion also. But we saw that switch capacitor voltage regulator actually suffer from poor line regulation, because if we take one cell of switch capacitor converter, we saw the peak voltage that we can achieve at the output is V in by 2. That means, if there is any variation in the input voltage, that peak voltage also varies. We also saw the ripple voltage, which depends on the load current. As a result, the average voltage, which is nothing but the peak voltage minus half of the ripple, that depends on that also depends on the load current. That means, if the load current increases, then the ripple increases, as a result output voltage decreases. So, it also suffer from poor load regulation and line regulation. Another important factor, that means, we generally, since we achieve the peak voltage is V in by 2 for one cell, if we want to set the output voltage much lower than V in by 2, then we need to allow larger and larger ripple, and that kind of ripple can also degrade the efficiency. That means, if you operate this voltage regulator duty ratio different than the V in by 2 for step down, for step up to V in, then it suffer from poor efficiency. So, for the best efficiency, we should operate close to the V in by 2 for one cell. That means, the voltage step up and step down generally we can achieve in a factor of 2 for one cell, factor of 4, like a factor of 2 to the power, sorry, a factor of 4 for 2 cell, factor of 8 for 3 cell, and so on. Hybrid switch capacitor converter, voltage regulator, they offer superior efficiency as well as regulation compared to pure switch capacitor converter, but of course, at the cost of inductance, which also decreases the power density. And whereas the pure switch cap we can go for fully on chip implementation, for hybrid switch cap, depending upon the inductance value, we may not be able to go always on chip. So, we need to keep the inductor outside the chip, and here also we can achieve both step up and step down conversion. Then hybrid switch capacitor voltage regulator, it require more switches compared to LDO. So, we need more switches. It also require, the flying capacitor voltage also has to be maintained, because if the flying capacitor voltage deviates significantly, then the regulation problem occur, and if you do not balance, because we are just showing a single stage step down conversion, and if you use multiple such stages, that means if you use multiple cells, say let us say you want to achieve a voltage step down of 1/8. So, you can connect 1 by 2, 1 by 2, 1 by 2 this in cascade, and this is very important to maintain the voltage regulation, that voltage across the flying capacitor, the voltage balance is very important. If you do not regulate, that can lead to, because the switches are designed based on the voltage rating. So, if there is a significant deviation across the voltage of the flying cap, it can actually deviate, it can lead to the voltage, the switch can actually go beyond its voltage rating. So, we have to keep that in mind, the voltage balance, voltage control of the flying cap is also important. The hybrid switch capacitor voltage regulator, these are gaining actually lot of attention for high step down, high step up operation, where we need to achieve high power density, smaller size, higher efficiency converter, which can achieve higher step down as well as higher step up, and these are the current research topics, and where the control and optimization is also a very important factor, because the voltage balancing issue, there are multiple issues are involved. Now, if we go to inductive DC-DC converter, which are primarily known as switch mode power converters, suppose if we start from our hybrid switch capacitor converter, where we have considered the flying capacitor to be the primary source of, like is the element for primary energy transfer process, is responsible, whereas inductor act like just a smaller inductance. It is the flying capacitor which takes the key role, which play the key role. Now, here we need 4 switches, 1 flying capacitor, 1 inductor. Now, if we replace this primary energy transfer element by inductor, and remove the flying capacitor and simply 2 switches are enough. But in this case, you have to keep in mind that the inductance value will be higher, because to maintain sufficiently like within an acceptable ripple limit. Okay. So, we need to this converter generally for the similar switching frequency, this hybrid switch capacitor converter, the inductance value can be reduced, and people talk about 3 level buck converter. So, where for the same switching frequency we can reduce the inductance value. Yeah, that means the smaller inductance can allow to go for higher switching frequency. So, purely inductance, pure inductor, actually these are known as inductive step down converter or buck converter, which is is a good example of switch mode power converter. If we take step up DC-DC converter, then the step up DC-DC converter actually we have input voltage, and again we start with a hybrid switch capacitor boost converter, where flying capacitor is actually responsible for energy transfer process, but the inductor we still use a small inductance. But now if we replace flying capacitor, that means with a pure inductor as energy transfer element, then it becomes a regular boost converter. This is known as DC-DC boost converter, where inductor is responsible for energy transfer from input side to the output side, because we want to achieve step up voltage, which is, that means output voltage is higher than the input voltage, and we need to operate switch S and S bar in such a way that we meet the desired step up performance. Again, in this case the inductor value requirement will be somewhat higher, and this converter is known as boost converter, and this is also a good example of is a good example of switch mode power converter. So, in summary, today what we discuss, that means we talk about linear voltage regulator, particularly linear dropout regulator, which uses the basic concept of resistive divider network, and these are suitable for ultra low power application, where use of switches, inductor, capacitor will actually increase the size of the converter. So, for very small size, very low power, still these linear regulators dominate in this segment. Maybe I am talking about less than a few milliwatt power level. Then linear regulators are not suitable when we are going for a little higher power, even for few hundreds of milliwatt, and of course few watts or tens of watt. These regulators cannot achieve step up voltage, it can only achieve step down. That means step up purpose cannot be achieved using this linear regulator. Then we discuss about pure switch capacitor converter, where the flying caps are used to achieve desired voltage regulation, and we saw the voltage can be achieved like a factor of 2 for one cell, for 2 cell factor of 4, and so, and such converters suffer from load and line regulation problem, and they are not suitable also for very high power. But now people are also thinking of going for a higher power application, because the switch capacitor converters are used for even multi-level converter as well. And hybrid switch capacitor converter, where along with the flying capacitor we consider smaller inductance, and such converters are gaining lot of attention nowadays for high frequency, like a high power density switch mode power converter, where we can achieve much smaller power supply, we can design a much smaller power supply using a hybrid switch capacitor architecture, and this is an emerging area of research. But still there are a lot of aspects like a optimization, modulation, voltage balancing, those need to be addressed. And finally we discuss about inductive DC-DC converter, which still dominate in most of the commercial product, and in this course we will primarily consider switch mode power converter in particular, and we will discuss about modulation, control, modeling technique of this switch mode power converter. So, we will take the switch mode power converter somewhat in depth discussion in the next lecture. Thank you very much.